In this lesson, we're going to explore long-term population data and discover why simple exponential growth models fail to capture real-world dynamics, leading us to Verhulst's logistic model. Let's start with the historical context. In the late 1700s, Thomas Malthus proposed that populations grow exponentially when resources are abundant. The Malthusian model says that the rate of population change equals R times N, where R is the intrinsic growth rate and N is the population size. This differential equation has the solution, N of t equals N sub 0 times e to the RT, which is pure exponential growth. This model works remarkably well for early population data, but it has a fatal flaw that becomes apparent over longer timescales. Let's examine real data. We'll use United States Census data from 1790 to 1990, spanning 200 years of population growth. Here's a subset of the data. Notice how the population starts at 3.9 million in 1790 and grows to nearly 249 million by 1990. The growth appears to slow down in later decades. Here's an important question. Does exponential growth adequately describe this entire dataset, or do we need a more sophisticated model? Our strategy will be to fit the exponential model using only early data from 1790 to 1890, then test its predictions against the held-back data from 1900 to 1990. This is a classic train-test split used in data science. We train on early data and validate on unseen later data to assess model quality. Let's fit the exponential model to the training data from 1790 to 1890. We need to estimate two parameters, N sub 0, the initial population, and R, the growth rate. Taking the natural logarithm of both sides gives us ln north equals ln n sub 0 plus RT. This is a linear relationship, which makes fitting easier. We perform linear regression on the logarithm of population versus time. The slope gives us R, and the intercept gives us ln n sub 0. From the data between 1790 and 1890, we obtain R approximately equals 0.0294 per year, or about 2.94% annual growth. The initial population N sub 0 is approximately 3.9 million, matching the 1790 census value. How well does this exponential model perform on the training data from 1790 to 1890? Here's the training data plotted with yellow dots, and the green curve shows our fitted exponential model. The fit looks excellent on this early data. The answer is yes. The exponential model fits the early data remarkably well. But now comes the critical test. Now let's extend our predictions to the held-back test data from 1900 to 1990 and see how the model performs. The red dots represent the actual test data from 1900 to 1990. Notice how the exponential model in green consistently overestimates the population in later years. The exponential model fails dramatically on the test set. By 1990, it predicts over 400 million people, while the actual population is only 249 million. This raises a crucial question. Why does the exponential model fail? What biological or ecological reality is missing from our mathematical description? In 1838, Pierre-François Verhulst proposed a revolutionary idea. Populations cannot grow indefinitely because resources are finite. As population increases, resources become scarce. Competition for food, space, and other necessities slows down reproduction and increases mortality. The carrying capacity, denoted K, is the maximum population that the environment can sustainably support. Verhulst modified the Malthusian model by multiplying by the factor 1 minus n over k. This is called the logistic differential equation. Let's understand what this extra factor does. When n is much smaller than k, the term 1 minus n over k is close to 1. When population is small compared to carrying capacity, the logistic equation reduces to exponential growth. This explains why exponential models work early on. But as n approaches k, the growth rate slows to 0. The population levels off at the carrying capacity rather than exploding to infinity. The logistic differential equation has an analytical solution that we can use for fitting. The solution is n of t equals k over the quantity 1 plus the quantity k over n sub 0 minus 1 times e to the negative rt. This is the logistic growth curve. This equation produces an S-shaped curve. It starts with exponential growth, then transitions to slower growth, and finally saturates at the carrying capacity. Now we need to fit three parameters, n sub 0, r, and k. We'll use the same training data from 1790 to 1890. Unlike the exponential model, we cannot linearize the logistic equation easily, so we use nonlinear least squares regression to find the best parameters. The fitted growth rate r is approximately 0.0313 per year, slightly higher than the exponential model. The estimated carrying capacity k is approximately 389 million people. This suggests the U.S. population will level off around this value. The initial population remains 3.9 million, consistent with the 1790 census. Now let's compare both models on the complete dataset from 1790 to 1990. This is the moment of truth. The green curve is the exponential model, the blue curve is the logistic model, and the orange dashed line shows the carrying capacity at 389 million. Notice how the logistic curve in blue tracks the actual data much more accurately, especially in the later years. It captures the bending over and saturation that the exponential model misses entirely. Let's quantify the model performance using mean squared error on the test set from 1900 to 1990. Mean squared error equals 1 over n times the sum of the squared differences between predicted and observed populations. The exponential model has a mean squared error of approximately 8,640 on the test set, with units of millions squared. The logistic model has a mean squared error of only 186, which is over 46 times smaller than the exponential model. The logistic model reduces prediction error by more than 98%. This is a dramatic improvement that cannot be dismissed as statistical noise. This superior performance raises an important question. What does this mathematical success tell us about the biological and ecological reality of population growth? The success of the logistic model provides strong empirical support for Verhulst's hypothesis about resource limitation and feedback. The data clearly show that exponential growth is not sustainable indefinitely. Real populations experience constraints that slow and eventually halt growth. As population increases, negative feedback mechanisms kick in. These include competition for food and space, disease spread in dense populations, and behavioral changes. The carrying capacity is not arbitrary. It emerges from the finite availability of resources like arable land, water, energy, and food production capacity. The logistic model embodies density-dependent regulation, where per capita growth rate decreases as population density increases. This is a fundamental principle in population ecology. While the logistic model is a major improvement, we must acknowledge its limitations and discuss more sophisticated extensions. In reality, carrying capacity changes over time due to technological innovation, resource discovery, and environmental changes. The model assumes K is fixed. Human populations undergo demographic transitions where birth rates decline even before resource limits are reached, due to cultural and economic factors not captured by the simple logistic equation. The model treats the population as well mixed and closed. Real populations have spatial structure, migration, and heterogeneous resource distribution. Ecologists have developed extensions like the theta logistic model, alley effects, and age-structured models that capture additional biological complexities. Let's summarize the key findings from our analysis of long-term population data. The exponential model provides excellent fits to early population data, but systematically overestimates later values, failing the out-of-sample prediction test. The logistic model, which includes a carrying capacity and density-dependent feedback, accurately captures the saturation observed in long-term data. The dramatic reduction in prediction error provides strong empirical support for Verhulst's idea that resources and feedback limit growth. The answer to our original question is clear. Populations do not grow exponentially forever. Resource constraints and ecological feedback are fundamental features of real population dynamics. This analysis illustrates important principles that extend beyond population biology. Models that fit training data perfectly may fail catastrophically on new data. This is why validation on held-back test sets is crucial in any predictive modeling exercise. Models grounded in biological or physical mechanisms, like the logistic equation, often generalize better than purely empirical curve fits. Mathematical modeling can reveal fundamental constraints and organizing principles in natural systems that might not be obvious from casual observation. The scientific method demands that we test our models against new data, remain skeptical of overly simple explanations, and refine our theories based on empirical evidence.